Okay, here's a question for you. How do you get people and equipment into these extreme polar regions? How do you land an 80-ton plane on a block of ice? Well, that's where the sandbox comes in. David, our teachers are going to play in the sand?
They're going to play in the sand. The answer to your first question, of course, is you land that plane gently somehow. That's exactly right. But we're going to play in the sandbox here to get some idea about pressure on flat surfaces.
That's the key, huh?
That's the key.
Okay.
So let's go for it. Okay. All right, what we've got here is a sandbox. It happens to be placed in a large pool just to keep the sand contained in your classroom environment or wherever you happen to be doing the activity. And the activity is titled, The Pressure is On. It's one of the activities in the packet. We're going to begin by just having a couple volunteers from the group come up with their specially selected shoes. Come on forward. If we've got a surface of sand, it's soft, right? And as we stand in it, what do you think is going to happen? We're going to sink, or basically leave a footprint of some kind, right? Now, just looking at the three volunteers as they stand here handsomely, who do you think will sink the most? Sam, you won! Yeah, right. Yeah, well, they think that Sam's going to sink the most, and why do you think that? Because he weighs the most, and we won't get into the details here, but Sam, people think you weigh the most and you're going to sink the most. Do you think that's true?
Yes.
Okay, you agree with that. Who do you think is going to sink the least? They're looking. Yeah, right. Well, without further analysis here, it has a little bit to do with their weight. I can see you already sort of doing some analysis there. Do you think it has anything to do with what they're wearing on their feet?
Yes.
Oh, well, let's hold up these special shoes, if you will. There's Tessa's. Tammy, hold yours up. Sam, hold yours up. Take a look at those shoes. So now, looking at the shoe, which do you think is going to sink the most? You think Tessa's going to sink the most relative to her shoe design. Now, the trick is balancing this weight and the surface area questions about the shoe itself on the surface of the sand. So we've sort of done some predicting. Let's try this. Tess, let's make footprint right here in this space, if you would, with that high heel shoe. Put all your weight. You can use my back or hand if you like. All your weight on that shoe. Ta-da! Okay, step back. One of the things I did was I moistened the surface of the sand a little bit before we started the activity. It's something you might want to keep in mind just to make that hold its form a little bit better. I guess the real question I would ask you is, if you were going to walk on a thin ice surface, what shoe would you like to be wearing? Not high heels. Say nothing for the slipperiness here, but the reality is you'd like to have a pair of Sam shoes there to work with. Yeah. In this second part of the activity, the materials that you'll need are a pencil or writing utensil, graph paper with, if you can, 1-inch square spacing on the graph paper, and a calculator. What we're going to be doing here is we're physically going to be calculating the pressure from our footprint. This is the equation we spoke about earlier. Pressure is equal to the force divided by the area. The force in our case is going to be our weight in pounds, and the area, of course, will be calculated in square inches. Richard, if I can get you to corral and observe this side of the group, and I'll take care of this side of the group, we're going to be tracing our footprint on this graph paper and roughly adding up these numbers of square inches contained in that footprint. And then using the calculator, divide the weight, your personal weight, and we don't have to know exactly what that is, but you can just punch it in the calculator and divide it by the number of square inches, and we'll get pounds per square inch. Some of you with larger footprints have actually taken 2 pieces of graph paper and taped them together. That's a good idea if you've got large foot students in your classroom. Any questions?
You promised this gets back to a big plane landing on ice, right?
Yeah, well, planes with lots of footprints, huh?
Okay.
Well, very big footprints.
There you go.
We'll get there, Richard. Trust us. Okay. It's that hands-on thing that we're engaged in.
Here we go.
All right. You take that side and I'll take this side. Let's begin. Folks, this is a good thing to point out. Remember, in a shoe print, we're really just putting a trace around the part that's in contact with the paper. So the toe and the heel are often separate from that. There aren't very many shoes that are entirely flat on a surface. This is Sam's footprint. We saw it earlier in the sand. And Sam, your PSI by calculation is?
8.87.
8.8 or 8.9 PSI, pounds per square inch. Okay, so fortunately your shoes spread that weight out a little bit. Let's take a look at well, let's do this. We'll do the 3 that we started with in the beginning. Here's that high heel shoe of Tessa's. You can see the main part of the toe plate here, and then that little sharp heel. What was your PSI?
It was 15.8.
15.8, almost 16. So it's like almost twice what Sam's was. How can that be? How can you get a different pound per square inch from Tess than you would Sam? In fact, a larger one.
Much less area.
Much less area on the shoe. That's exactly right. So even though she may weigh less than Sam, if you minimize the surface area upon which that footprint is placed, you're going to get a much higher pound per square inch. We had a similar situation down here. Tammy was another one of those shoes that we looked at earlier. Here's the toe plate and a larger heel, but still a pretty sharp one. Your PSI?
11.8.
11.8, so it's somewhere in between the two. But the big comparison here, of course, is, again, with her partner. It's not safe. Very big footprint here on Ed's part. Ed, what was your PSI?
4.6.
4.6. Ed could walk across ice. All right. So he could make his way across that ice, perhaps. Going back to this PSI equation now, let's think about these big airplanes. Richard, are you ready?
I'm ready.
This is that C-130. Have you ever seen a C-130?
They drive trucks on those
Absolutely. They'll drive vehicles right into the back of these airplanes. They're very big airplanes. So when you land one of those on an ice surface, somehow we've got to get some big tennis shoes going here. We've got to spread out that surface area on the ice. How can we go about doing that?
Large skis.
Large skis, large tires. The tire mechanism on a normal C-130 brings the PSI to about 120 PSI, pounds per square inch. Now, if you're on a sheet of ice, 120 pounds per square inch is pretty heavy, and it might not work. So to spread that out, one of the things they use is skis. And they can spread that PSI down to about 40 PSI using skis. Larger surface area, big flat surface, it's like the big flat tennis shoe. That's how you land an 80-ton plane on a sheet of ice, Richard.